Welcome back to Math 31. This is a lesson on domain and range, the third actual lesson on it, and the final one. We'll be going through about half a dozen or so domain and range type problems, algebraic ones, such as we were doing before, slightly more complicated though. So to start with, we have f of x is equal to negative 2 over square root of x plus 2. The method will always be the same. For the domain, we isolate the y, which it is already, and then we go to work on identifying any restrictions. So we take a look at this square root of x plus 2 on the denominator, and that's the thing that we're concerned with. So we've been here before. X plus 2 has to be greater than 0. It cannot be equal to 0 because then it would be, the denominator would be 0. So x is therefore having to be greater than negative 2. So you have to watch out that special case. So this would be written as negative 2 all the way up forever. Then the range. Now you might recall from the previous lesson that we consider two things. One, we do the algebra, but that usually isn't enough. So we have to also watch out for sort of by inspection. And by inspection, in this case, when I see the numerator as being negative, and then because it's negative 2, and the denominator is square root of x plus 2 must be positive, because that's the positive root of x plus 2. So this means that this y value is always going to be negative, a negative divided by a positive. So y therefore must be less than 0. Now I'm still going to do the algebra on this by isolating the x and see if that gives us any more insight. But we have to be aware of a built-in restriction on the equation. So I multiply both sides by root of x plus 2. And then I get root of x plus 2. I divide both sides by y. This is good enough, actually. But even if you did take the time to square both sides and solve, we'll get x plus 2 is equal to 4 over y squared. And I'm going to stop there and just pay attention to the denominator, which is that y squared cannot be equal to 0, so y cannot be equal to 0. Well, we already know that based on what we saw before. That doesn't give us anything new. Y is less than 0, cannot be equal to 0. So the range could therefore be written like this, open interval. Number 6. Here too, or here, you probably already know what the graph looks like. And I haven't been graphing these ones deliberately just because I want to rely on the algebra. However, it's certainly within your right to graph these ones to check your answers. But I would use it as a check. Don't do it to start with. This is a parabola with two translations on it. But if we were to do this one algebraically, first off with the domain, and play dumb with this, like we don't know what it looks like. The x plus 1, there are no restrictions. There's no square root. There is no denominator. The range, well, if you isolated the 4, or the x, excuse me, add on 4, so y plus 4 is equal to 2 times x plus 1 squared. Then divide by 2. And then take the square root of both sides. And then we notice, we don't need to go any further because I don't care particularly about where that x plus 1 is, but y plus 4 must be greater than or equal to 0. So y is greater than or equal to negative 4. And that would mean we could write this as negative 4 all the way to positive infinity upwards. And if you did graph this one, it is a really rough sketch. I'm not going to take the time to do much with it. We have a vertical translation of 4 down, horizontal translation of 1 to the left. So, in fact, our graph is going to look like this, a parabola, somewhat of that form. So it's not too surprising then that we get that particular range and that particular domain. Try a few more. Now, number 7 is a similar form to what we've seen, a little more complicated though, at least as far as the range is concerned. The domain, all we care about is that denominator. It cannot be equal to 0. So x cannot be equal to 2. So in interval notation, we would indicate negative infinity to 2 in union with 2 to positive infinity. And then the range. We isolate the x, but it's a problem because we have two x terms. So when we multiply both sides by x minus 2, we get y times x minus 2 is equal to 4x. So yx minus 2y is equal to 4x. So I had to distribute the y in because there's no other way that I can gather these x terms up. So it wouldn't have been enough just to divide by y because we have to have the x variable isolated fully. We can't have an x on both sides. My next strategy is I'm going to take the 2y over and I'm going to gather up the x terms. So this becomes yx minus 4x. And now I can factor the x out, leaving me with y minus 4 is equal to 2y. So x is equal to 2y divided by y minus 4. And now we can see that for the range, y minus 4 cannot equal 0, so y cannot equal 4. So in interval notation, negative infinity to 4, open interval, in union with 4 to positive infinity. And there is our range. Now the next question, number 8, is a more complicated one still, and it can be a real problem. Y is equal to 9 minus x squared. Now this, by the way, is a semicircle, and once you've seen a lot of these, because they show up once in a while, you are able to go from A to B fairly quickly. If you haven't, you just do it straight algebraically, then we got a little more work. This involves inequalities, which is actually the next review topic, but we can get by without much knowledge. So the domain, I take that 9 minus x squared underneath the radical, and I note that it's got to be greater than or equal to 0. Now when I isolate the x squared, I'll bring the 9 over to the other side. And then I divide by negative 1 to get rid of that. And when you divide by a negative, you must remember to reverse the inequality. Now I will review all these rules when we get to the next unit, or the next module. But that's something you've undoubtedly seen before. Now the next thing is, when you get to x squared is less than or equal to 9, you need to remember that this is an inequality, not an equation. So the normal instinct is to take the square root of both sides and say x is less than or equal to 3. And it's not quite that simple. So I'm going to encourage you now. I don't normally encourage people to do this, but stop and think. X squared is less than 9. It means two things. It means x is less than or equal to 3. Most people are comfortable with that. But it also has to be greater than or equal to negative 3. Because you need to deal with the negatives. And if you took a number like negative 4, for example, negative 4 squared is positive 16. It's outside that. It's greater than 9. So you need to watch out for both the plus and minus with this. And it means that in interval notation, we would write that as negative 3 to positive 3. So be careful with that. You've got to consider the negative. Then the range. Now the range, by inspection, we can tell that y has to be greater than or equal to 0. That's based on this. It's the positive root. We need to do more, though. So let's see, with the algebra, if we squared both sides, we would get y squared is equal to 9 minus x squared. And if you isolated the x squared, I'll bring it over to the left to make it positive. I'll get 9 minus y squared. And then we take the square root of both sides, and this is going to start looking really familiar. Because plus or minus the root of 9 minus y squared, it's exactly the same as what we had for the domain. So I'm not going to do the math again. It would be the exact same thing. When we solve for 9 minus y squared being greater than or equal to 0, we will get negative 3 is less than or equal to y, which is less than or equal to positive 3. But the problem is, it also has to be y is greater than or equal to 0. So we need to consider both of those. The word and actually implies it satisfies both conditions. So we need to find the numbers that are both greater than or equal to 0 and that are also between negative 3 and 3. And it means that the restriction is going to turn into simply 0 to 3. So those numbers between 0 and negative 3 do not satisfy both equations. They must be greater than or equal to 0. So that's going to be the restriction on that. So a little bit trickier. There are some in the homework module, though. Now, number 9 is similar, except that the equation's a bit different. This is a composite function, meaning that there's a function within a function. And a couple tricky things happen here. For the domain, x squared plus 1 is greater than or equal to 0. So x squared is greater than or equal to negative 1. Now this is not an equation again. You can't just take the square root and take an answer because in fact you can't take the square root of negative 1. So here again we stop and think. And stopping and thinking in this case is going to mean we recognize that any number, when you square it, becomes positive. So therefore, any number would do for x. X will be an element of the set of real numbers. Pick a number, square it, it will be bigger than negative 1 because it's going to be positive. Then we turn our attention to the range and we note that by inspection y must be positive, greater than or equal to 0. Square root, it's the positive square root. But when we do the algebra, we write this as y is equal to the square root of x squared plus 1. We square both sides. So y squared is equal to x squared plus 1. So therefore, y squared minus 1 is equal to x squared. So x, when we take the root of, is equal to plus or minus the root of y squared minus 1. Now, when we set this to 0 and make our conclusions based on it, y squared minus 1 is greater than or equal to 0, so y squared is greater than or equal to 1. And this is like what we saw in the earlier example, because it's similar to it at least. It means that y must be greater than or equal to 1 to be when we square it greater than 1. But we also have to be aware that y could be less than or equal to negative 1, because negative 1 squared is positive 1, negative 2 squared is positive 4, greater than that 1 value. The problem is we also have to satisfy y is greater than or equal to 0. So this is impossible. You cannot be both less than negative 1 and greater than or equal to 0. So we have to take these two together. We look for the numbers that are both greater than or equal to 1 and greater than or equal to 0. And this will then give us simplified that y has to be greater than or equal to 1. Those are the only numbers that are both bigger than 1 and bigger than 0. Can be a problem. Now the next two are not real problems, except they're kind of special case ones. So I'm going to indicate this as a special case. It is an easy question. Excuse my writing. Seems to be getting worse all the time. I would say that sketch this one. It is a familiar graph. It's just a absolute value function. A rough graph, but with a x-intercept of 4, like that. And then we can see that the domain will be all real numbers. There's no restriction. Now, we could have recognized that from the beginning, right? Absolute value of x minus 4, you can plug in anything you want. And then the range, well, this is a bit of a problem. We know it's going to be positive, but we don't know how to simplify algebraically that absolute value yet. In fact, we do learn that next module. But what I would suggest we do for this one is just base it on the graph that y is greater than or equal to 0. So 0 all the way up to positive infinity. So really my advice for these ones is that you are trying to get the answer by whatever means possible. On exams, you're often asked to do it algebraically. But a question like this, you wouldn't be, because the idea really is that you know that this absolute value graph is looking like this, so you don't have to worry about it too much. You know what it looks like, and then you make the conclusion based on that. Similar with number 11. Now the domain is not a problem because it's the square root. So we get x, the root of x tells me that x must be greater than or equal to 0. Now the range, I'm also going to use simple reasoning power, because the algebra is a little tricky on this one. So what I would recommend is that you think about what the graph looks like. A square root graph with a vertical translation of 2 upwards. So in fact, the range is y is greater than or equal to 2. So 2 upwards forever. And it kind of makes sense, because if you take a look, the smallest value for x, is 0. And if x is equal to 0, then y will be equal to 0 plus 2. So the lowest value you're going to be is positive 2. So do not turn off that sort of reasoning power of your brain for these. Where algebra breaks down, you still want to get an answer, and you can sort of trust your knowledge of the graphs. Now, the very last one, y is equal to the square root of 2 minus root x. This is a bit of a problem one, and in fact, we just want the domain. Because we have this together. Now we have the double radical, so it doesn't matter which one you take a look at first. I'll take the outside radical. So 2 minus root x has to be greater than or equal to 0. We know that because that's the nature of square roots. Bring the 2 to the other side. We get minus root x is greater than or equal to negative 2. Now I'm going to divide by the negative again, giving me negative root, or giving me root x is less than or equal to 2. And this one is kind of a stop and think type question, but if the root of x is less than or equal to 2, it probably makes sense for you that x must be less than or equal to 4. But the other thing is, the root of x, we cannot take a number bigger or smaller than 0. So the lower limit is 0. So we end up with just this, 0 to 4, a closed interval. And really, who knows what the graph looks like? You'd have to graph it to find out. But you're not expected to know what it is looking like beforehand. Now that's going to take care of it for this one. The next lesson will be on obscure operations with functions. Thank you for your time.